Okay, morning everyone. We'll start off today just with a couple practice questions here just for warm-up. So, first one, just practicing drawing a structural isomer. So see if you can draw this molecule for me here. 4-ethyl, 2,6-difluorooctane. Okay, see if you can take that IUPAC name and draw the structure. Keep things nice for yourself, draw things nice and straight and not kinked up on yourself here. Keep the numbers as tiny as possible and then just sub on these substituents here. We talked about structural isomers in our previous lesson, so let me just give you a small one here. Draw all structural isomers. Let's just do C5H12. So not as many as we've seen in previous examples, but just gives us a feel of how we did from yesterday's stuff. So again, I encourage you just to pause the video, try it out for yourself here, and then when you're ready, just unpause and then just check the work here. So starting off here, we're drawing this molecule here. I'd start off with the very last part in the name. So this one here is supposed to be an octane. Oct means 8. So let's just draw 8 carbons in a row. Okay. Because the numbering is totally up to us, we're just going to, for simplicity, just number things left to right. Octane is understood to have a bunch of hydrogens. Sometimes they try to scare you by showing, oh, there's a hydrogen substituent. Well, we had assumed that there's hydrogens there anyways. And it's just there are a couple places here. At position 4, we sub on an F. F implies 2 carbons. So you can either draw both carbons in a row like that. You can do the condensed structure. Ethane would normally be C2H6, but remember I need to have one arm to actually hold on to the parent, so I could say that as C2H5. We'll see that a little bit more in today's lesson. Doesn't matter whether it's on top or bottom. And then the difluoro, this just means there's 2 fluorines somewhere in the picture. I should be able to find one of them at 2, one of them at 6. So at position 2, there's an F, and at position 6, there's an F. And it's understood that the rest are hydrogens. When you are sketching this here, very often they're just going to write this part here. Let's say CH3, just imply the other hydrogens there. They might just say CH here, just to imply, well, carbon has 4 extra arms here. It has 1 arm holding hydrogens because the other 3 arms are currently being used. And that's another way of sort of condensing the hydrogen parts here, just showing the most important bits. For the structural isomers question here, not as difficult because we're all just dealing with just carbon branches here. Still, we do it very systematically here. We had done probably a harder one in yesterday's lesson when it had a different substituent, but starting with the N, the straight chain one. So this one here is just going to be plain old pentane. So 5 carbons in a row. Okay. We're going to systematically here, let's remove 1 carbon at a time. Let's see where I can put that carbon. So that would be now 4 carbons in a row. We talked about here for carbon alkyl groups here, carbons cannot go on the ends, or else that's just a slightly kinked up version of a 5-carbon chain. The carbon at the very least has to be in the middle of the chain. So here we have a 2-methyl that's branched off of butane. Okay. We could have tried putting this carbon here on what would have been position number 3, but being the only branch, I would have counted the parent the opposite way here. That would also be 2-methylbutane. That's the only one that I have. Okay. So that's the only methyl substituent isomer that we have. Let's imagine cutting off another one. So now I have the flexibility of playing around with either 2 methyl groups or 1 ethyl group, playing off of a 3-carbon chain. Again, we're really restricting our attention a little bit here. Well, carbons can't go on the end, so I could potentially have an ethyl group on the side. Okay. But as you saw in yesterday's lesson here, well, that would still be a butane. It'd be a 4-carbon, 2-methylbutane. Well, we had that. Same name means same isomer. So it can't actually be an ethyl group, but it could very well be a 2,2-dimethyl. In that case there, the longest chain you can string together is 3 carbons. I can just show you here. Let's say I'm doing this parent here on the top here. That would still be a 2,2-dimethyl propane, just like we had seen if I had done the left to right parent here. So 2,2-dimethyl prop for 3, so propane. Okay. So far, we've just been in the alkane family. Everything is just plain old all single bonded. We started doing these substituents, these branches off the parent here. Today, we're going to introduce one other variety that can happen to these. It is actually ending up forming a ring in what's called cycloalkanes. Okay. But aside from that here, it's not 2,2 challenging in comparison to what we've already been doing. So cycloalkanes, okay, sometimes they refer to these here as cyclic compounds, all just names for things are forming rings. Okay? So the smallest ring we can form is having 3 carbons. You can imagine 2 carbons holding each other already. It's already just going to be just a straight molecule there. But hypothetically, we could have 3 carbons in a row. Let me just actually sketch for you all the hydrogens, just so that we can keep track of the condensed formula, how many hydrogens should be attached to there. Okay. That one there, again, sometimes you'll see this prefix N. Not usually for really short alkanes like this, because if I have 3 carbons, they're probably going to be in a row anyway, so no branches or whatnot. The parent is just going to be the 3 carbons in the chain. This molecule is currently C3H8. If you count up the number of extensions there, hydrogens saturate. The word saturate just means fills up. Okay. It's possible, though, that these 3 carbons here, instead of being terminal, instead of being on the ends, I could actually ditch the 2 hydrogens that I'm currently holding on, and I can actually bond these 2 together. So what that would look like here is there would be 3 carbons in a ring. Okay. Again, carbon is very nice. It has 4 unpaired electrons. It should be able to make the equivalent of 4 bonds. You should always be able to spot where all 4 of the unpaired electrons went. That means this carbon here has 2 extra hydrogens. They're holding 2 other hydrogens there. I can summarize them as H2. If they write H2C, exactly the same thing. They're just implying that the hydrogens are on the left-hand side there. Okay. So there we go. We have a ring compound. It's cyclic and whatnot. First question, we just learned this term here, structural isomers, from yesterday's lesson here. Is this molecule that I've just drawn, is it a structural isomer of the N-propane? Well, to be a structural isomer, iso meant same. It has to have the same molecular formula. If you've been following along here, you saw that I had to ditch 2 hydrogens here, which means in total here, I actually only have 6 hydrogens left. I have C3H6, because these ones here are not the same molecular formula. Let's just make a note here. These are not structural isomers. Okay? They would have to have the same formula if they wanted to be structural isomers. However, as we start looking at the IUPAC name of this one here, well, they're not isomers of each other, so we expect it to have a different name. This is a compound which actually has a ring. It's cyclic, okay? But it still has 3 carbons in the chain. So we'd like to preserve this prefix here of propane. It's just that, as I wrote earlier here, we're going to add this term here, cyclo, in front of it, just to remind me that these carbons here have actually formed a ring. So we're going to call this one here actually cyclo for the ring, but it's cyclopropane. We have the 3 carbons in a ring. Okay. As we start looking at larger and larger rings here, these rings here are not necessarily flat, okay, but if you try to imagine this as a flat chain here, this is actually not really good for it. Earlier here, having 4 bonds here gives us that tetrahedral geometry we saw before. The angle is 109.5. If I were a perfectly flat ring here, we're looking at angles like 60 degrees. Remember, these ones here are electron domains. There's areas, there's clouds that are negative. Negatives hate each other. They just keep pushing away from each other here. These 2 bonds here are just waiting to snap apart at any given time. So while you can form the cyclopropane here, it's not super stable. At the very least, we'd like to be maybe 4 carbon chain, 5 carbon chain here. Let's get the ring size to be a little bit larger. Let's get this angle to be a little bit bigger so it doesn't snap open on you. Okay. So let's just practice another one here. Going from butane. Okay. So butane we had. I always just start off with this just a straight chain. I imagine things are not cyclic. I imagine that they're not rings just yet. And again, just like we saw previously, instead of the terminal carbons holding an extra hydrogen, we need to ditch these 2 here. Every time I form any ring, I can have a molecule which has multiple rings, but every time I form a ring, I'm always going to lose 2 hydrogens on the end. So we'll just make a note here. We're going to lose 2 hydrogens per ring. Just for simplicity, we're only going to be dealing with compounds with 1 ring, and the ring is always going to be the parent for us. So imagine for us here, we're going to have 4 carbons in a ring. Again, not necessarily perfectly flat and square and whatnot, but steadily we're starting to see that this angle is a little bit bigger. It's not going to snap open as easily as that 60 degrees you saw earlier. As I'm forming a ring here, we don't have any terminal carbons anymore. All of these carbons here only hold 2 hydrogens. Again, not a structural isomer because I have now C4H8, but name-wise, when I'm looking for the longest chain, we're only going to have 1 ring. The ring itself is going to be the parent, and all we need to remember is to emphasize the ring part, we're going to use the prefix here, cyclo. Okay. So if it's just plain old butane, it's straight chain. If it has that word cyclo, this thing here has ended up forming a ring itself. Okay. It's totally possible that this is so far just an alkane, a hydrocarbon, just plain old C's and H's. We could substitute this just like we did before. Okay. So let's just try another molecule here. This is where maybe even skeletal formulas, just showing the structure of it might be a little bit easier to look at. Okay. But let me just sketch a bunch of these carbons here. And let's say instead of the H2, let's say I sub on an I group over here. And let's sub on a Br group on the side here. Okay. Again, just for simplicity, our molecules will always only have one ring. Okay. The ring by itself is always going to be the parent. Even if I had, like, let's say a methyl group or whatnot, I don't count, let's say, like, oh, this carbon is adding to a 6-carbon chain. No, the ring by itself is just going to be the parent. Okay. That's going to be the longest chain here. We need that prefix cyclo to tell me that's a ring. And then that HO question here, well, being a circle, being a ring here, where does the circle start? We want to start position number 1 where the branches are tiny. In this case here, there are a bunch of hydrogens. I had imagined that the rest of it would be saturated with hydrogens anyways. They're emphasizing these are H's. I don't need to name those bits, right? I imagine they're hydrogens anyways. The parts that I swapped out, I replaced one of the hydrogens with an I, one of them with a Br. I'm going to start with one of the branches at position 1. It doesn't matter with Br or iodine, totally up to you. And then counting either clockwise or counterclockwise. If I count it clockwise, I don't get to my Br until I get to position 5. I want to actually count it, let's say, counterclockwise here, also called anti-clockwise, so that it's 1 and 2. Here's another example molecule where it didn't really matter. If I counted it the opposite way here, clockwise, I still have 1 at position 1, 1 at position 2. So take your pick. I know it's going to be a slightly different name. You might even imagine, oh, those are structural isomers. No, it's just a one molecule. But given that neither of these really take priority, either the names are IUPACly correct. Okay, so let's say, for example, I take the numbering in green. Bromo, Br, B comes before the I. So at position 1, we have a bromo. At position 2, so hyphen, we have an iota group. And then before you're going to say pentane, if I just say the word pentane, it means 5 carbon in a chain. To emphasize that this is a ring, we're going to be a cyclopentane. Okay, so just simply this prefix here, cyclo, implies that things are a ring, things are cyclical, things are in a circle. Okay. What I'm going to emphasize here, this is so far, it's sort of a combination. This part here is sort of like a condensed formula. I've sort of shortcutted some of the hydrogens, but still showing you the carbon bits here. I'm going to start representing this using what's called a skeletal formula, or a skeletal structure. Okay, skeletal, like the name suggests here, it implies here just the skeleton, just the sort of bare bones of this here. Okay. We know the naming part just comes from the carbon bits here. A skeletal formula, I alluded to it previously here, it's going to have a corner wherever there's a carbon. So this is kind of nice. I'm going to have a bunch of these corners here. I'm going to form a nice pentagon ring. Okay. And then it's understood that the remainder of these are holding hydrogen. So I don't need to say, oh, by the way, H, by the way, H. I know that those are hydrogens already. Okay. I know that every carbon should have the equivalent of 4 bonds. So aside from the ones that I've sketched, so this is holding carbon and carbon, I know that 2 other arms are holding hydrogens already. The only parts I need to specify are the other grouping. So what's not hydrogen is an I group. So I'm just going to stick a bond out this way. I'm going to emphasize that there is an I there. If I just had a line and there wasn't an element there, I would imagine that there's a methyl group there. Okay, but in this case here, we happen to have a Br substituted here, and there we get a Br ring. Again, compared to the cyclopropane we saw earlier, as this cyclical part, this ring part here gets a little bit larger, this bond angle gets to be a little bit larger as well. Again, not necessarily flat. We call it, it's a puckered ring. It's actually like a kinked ring on itself. Okay. But we can substitute it just like we did in previous cases. If we can, we're going to keep numbers tiny. If I have the same branch, we use the di, tri prefixes again. And in this case here, if I have alphabetically here, the B for bromo comes before the I for the iota part. So for a skeletal structure here, if you need to just sketch it for yourself here, every corner Every corner is a carbon. Okay. So again, just for simplicity, I've drawn in all those red things there. I normally wouldn't even draw in that red for you there. Okay. And every side, if I have a branch off, I imagine there's a carbon. In this case here, because I tell you what's actually attached to it here, we know that that's not carbon. Okay. So hypothetically, again, just for simplicity, we only do one ring. The ring is always the parent here. Hypothetically, we could have a molecule that sort of kinks back and forth, okay? Really long carbon chain, okay? We could have a ring that's actually a little bit tinier, maybe that propyl group earlier, okay? Sure, it's still sort of simplified for us here. This molecule here only has one ring, okay? Normally the one ring would be the parent. If we were really looking at this though, we'd say, wait a second. If my carbon chain, if every corner is a carbon, okay? Well, that's a much longer carbon chain. I think that's 8 carbons long. There will be times where later on, if I have rings that are really tiny in comparison to long chains, you might see this group here referred to as a cyclo-propyl group. Cyclo for ring, and then the YL ending tells you, oh, it's a branch. Okay. Again, this is just, if you go on to chemistry here, you're going to see this, see multiple rings, see rings that are tinier and whatnot. For us, we're going to deal with more so the case, there's only going to be one ring. The ring is always going to be the longest chain, and you're going to actually just, using that as the parent, name the substituents, keep the numbers tiny, as you do normally anyways. Okay. So let's just practice another one here. Okay. Let's draw that skeletal structure. Okay. I'm going to draw like a stop sign shape, so it's an 8 carbon ring. Okay. I'm going to draw that, maybe that. Let's sub on a fluorine group, and let's sub on maybe another fluorine group here. Okay. So I know that doesn't really look like much. It looks very scratchy here. Okay. But that is the skeletal structure for a formula. Okay. Again, for our simplicity, we only have one ring. Okay. If it helps for you for starting off here, every corner and every kink is going to be a carbon. So normally I wouldn't draw these C's in. Okay. You see some of them actually are substituted. They're sort of branched off. If I tell you what this is just bonded to the one single fluorine group. If I have a leg out and I don't specify what it is, it's understood that there's another carbon group on there. And especially as you're counting the parent, as I alluded to already, you do not go, well, I know there's 8 carbons in a ring, but couldn't I go like 1, 2, like make it a 9 carbon chain? No, our ring is always just self-contained. That ring there is going to be the parent. Even if I had carbon chains, this time I don't have any side carbons, so I can actually attach these methyl or ethyl groups anywhere I want. Okay. And the last rule here is just keep the numbers tiny if you can. Okay. So usually what I like doing is I like starting with the very last word, the parent. The parent here is going to be the ring. That's going to be the longest chain, just self-contained in there. We said there's going to be 8 carbons, so we know it's going to be an octane. But for today's lesson here, what we're going to do is we're going to add the prefix here, cyclo, before our word octane. That cyclo tells me these 8 carbons aren't any old carbons. They're actually 8 carbons that actually form a ring-like structure. That covers in the blue there. And now we just need to name the remainder of the branches here. Well, the branch by itself, this branch is a 1 carbon branch. So let's call it a methyl. Remember, meth stands for 1. This one here, which is 1 carbon and then another carbon here, this branch by itself has 2 carbons. So this is going to be an ethyl branch. And then we happen to have 2 of the same branch here. These are fluoro. These are halides, halogen groupings here. We have 2 of the same fluorine branch, so it's going to be difluoro. Okay. We will at the very least start off with position number 1 at where a branch is, but seeing as this ring here has multiple different branches here, we want to make sure all the numbers are as tiny as we can get them. All right. So let's just try it out here. I see that these 2 branches are sort of side by side. So either I'm going to choose carbon 1, 2 going around counterclockwise. So that would be 1, 2, 3, 4. I have one at 5 and then 7. If I counted it the opposite way here, count this as position 1 and this is position 2, going the opposite way here, we have one at position 1, 2, 4, and 6. While counting this way here is slightly smaller, so we're going to choose the smallest way. Again, we count the smallest number. Just in case we're looking at this ring here from the opposite side, I want to, as much as I can, end up with the same IUPAC name. Okay? So I now have the numbers as tiny as we can get them. Last thing we do is we alphabetize. So it looks like the E for the ethyl comes first. Ethyl is at position number 4. So 4, hyphen ethyl. Okay. Then comes the two fluorine groups here. Because I have two of the same fluorine group, it's going to be a difluoro, still alphabetized for the F in fluoro. I still need to tell you where they are. So hyphen 1, 6 at position 1 and position 6. There happen to be one fluorine branch. Okay. The difluoro tells you there's two somewhere in the picture. Okay. Then lastly comes our methyl. Our methyl happens to come in early in the chain. That's fine. So we're going to have, let's just put it down here, 2-methyl. And usually, again, people usually ram this last branch here into the parent name. It's okay if you put a hyphen or not. But there we go. We've sort of packed in all the information into that name there. And really the only new bit here we're using here is this word here, cyclo. The cyclo reminds you that there's a ring there. Okay. So later on, even as we get into more complicated families with double bonds and triple bonds, they can also have rings. They're just going to be cycloalkenes, cycloalkynes. That word cyclo still stands for the fact that we are a ring. Okay. Again, lastly, just for practice, sometimes we're not given the structure all drawn out and all nicely diagrammed for you here. Sometimes we're given just a word name. We want to see if we can draw the picture. Okay. So let's see if we can go the opposite way here. Let's do a 1,4 dichloro. Okay. Just gives us a little bit more variety when we have our halogen groups here. 1,4 dichloro. Let's go 3, 3, 5 tripropyl. Okay. We haven't seen propyl groups all that much because we would have to have really long chains, or else the propyl group would end up extending the parent itself. But especially when I'm forming a ring, if the ring inside is just the parent inside, we can actually attach propyl groups anywhere I want. And then let's keep it as a ring here. So we'll say here cyclo, and let's do heptane. Okay. Right. Again, I usually find going this way is a little bit easier because I already have the word name. Okay, I'm just trying to draw the picture. Usually I start at the really end first. So we're looking for heptane. Hep means 7. We're still in the alkane family. Still everything's single bonded. Things are ending up forming a ring. So they're going to be cyclical or cyclo. So let's form 7 carbons in a chain. It doesn't need to be symmetrical. Okay. So let's just sketch a bunch of these carbons here. 5, 6, 7. Okay. Again, not necessarily going to be flat as well, but at least those bond angles look a little bit more relaxed than the triangle that we had earlier. Again, when it's up to us to choose which way we count it from, just pick one to be carbon number 1. Okay, you may not have chosen that top one as I did. Okay, but just count in one direction there. Okay, I would assume that all of these carbons are holding 2 hydrogen neighbors, except for these branches that they're saying. The dichloro tells you have 2 chlorines somewhere in the picture. Where are they? One's on 1, one's on 4. So branch off there, Cl. Branch off here, there's a Cl. Okay. And then 3,3,5 tripropyl. A propyl by itself is already a 3-carbon chain. The tri tells you you have 3 of these 3-carbon chains. Okay, lots of 3s here. Well, where is the propyl? One of them is on position 3. So position 3, you can draw 3 carbons like that. Okay. If you like, you can even condense it here. Well, we know if we're not terminal, we hold at least 2 hydrogens. This would have been a C3H8, but I had to lose an arm to glue onto this carbon. I could draw the other group, say C3H7 like that. These 2 groups are identical. You could have drawn 3 carbons in a row. Okay, not really worried about the geometry right now. And then position 5, also a C3H7. And again, as we're seeing examples of this here, we do not count the ring. Oh, our parent extends 1, 2, 3, and then into the ring. The ring by itself intact itself is the parent there. Okay. You always want to do a double check. Have I actually written the correct name here? Okay. So I've drawn it, no problem here. Okay. Well, say I had given you this picture. Okay. Would this actually be the correct name for it? Okay. Well, if we look a little bit closer here, wait a second. I actually have one special carbon here which actually has 2 branches, where these other carbons here only have 1 branch. So maybe I should have actually called this one, oh, maybe this is the wrong name here. We could draw it, no problem. I have all the chemistry that I need. But maybe I should have called this one here position number 1 instead. And then which way would I count it? So the numbers are tiny. If I count it counterclockwise here, 1, 2, 3, I would have a 1, 3. Here I have a 1, 1. If I count it this way, oh, maybe I should renumber this here. name is going to be very similar, okay? But maybe the numbers would have been better had the propyl groups here all been on 1, okay? So 1, 1, 3 instead, if you can see through my scribbles there. So maybe this should have been 1, 1, 3, would have been tinier numbers. And my chlorines are actually on 2 and 6 if you're counting around that way. So 2, 6. Totally okay if the numbers are sort of out of order because we're just alphabetizing the C for the chlorine, the P for the propyl. I know we're adding the di and the tri if I'm similar groups there, but keeping things simple, we just alphabetize based on the base name of that group there. So let me just end off here, just drawing the skeletal form of that structure here. This is sort of a lazy way of doing it because I'm sort of saying, oh yeah, everything is saturated, everything is packed full. You imagine that there's hydrogens that are attached to these ones here. But for a full structural formula, you should actually show me all those hydrogens. The sort of saving grace here is going to be the skeletal structure. Let's see if I can draw sort of 7 carbons in a ring. So 1, 2, 3, 4, 5, 6, 7. So let me double check here. 1, 2, 3, 4, 5, 6, 7. Okay. We have 1 that's holding on to chlorine. I know chlorine here does start with a C, but that's not a carbon. It doesn't belong to the parent at all. There's a chlorine off this one here. Okay. I assume that the remainder are going to be hydrogens. And then these propyl groups here, because there's sort of 3 in a row, I just kink it 1, 2, 3, 1, 2, 3. And then there's 1 on this end here. 1, 2, 3. Okay. So that's how my skeletal structure would look like. Okay, I just leave it what's in the black here. And what's understood is every time I have a corner, so I wouldn't normally draw in what's in the red here. Every corner there's a carbon. We have a group that's just one ring is the one parent. And as I kink it back and forth, 1, 2, 3 is going to be a propyl branch. Here's another propyl branch. Here's another propyl branch. Well, wait a second. Every carbon should have the equivalent of 4 bonds here. Again, it's understood. Hey, this carbon here is already holding 2 carbon neighbors. That means I'm holding 2 hydrogen neighbors. This is holding 2. This is holding 3. It's understood that the remainder are holding hydrogens. And just a reminder again, halogens here, they are not carbon. So not only do they not add to the parent or whatnot, they do not hold other hydrogens there. Okay. So a common problem I see people do, accidentally people go Cl and the H3, forgetting the fact, wait a second, this is a halogen. It shouldn't be able to hold any hydrogens here. It does have outermost electrons, but those are actually just lone pairs. It is just the one single chlorine atom that's substituted. That's the branch off this parent here. Okay. So your worksheet will have a little bit more practice with this. Pretty much we just introduced that prefix here, cyclo, when things are a ring. Thanks, everyone.